Unit Operation Classroom. Today we're going to discuss steady flow energy balance for an ideal gas mixture. My name is Shekhar Bhattacharjee. A gas mixture of 50 weight% argon and 50 weight% helium. Uh, weight% is the same as the mass percent. And of course, this is very unusual to express the gas phase composition in terms of weight% or mass%. Normally, they're expressed in volume% or mole%. But anyway, this is the problem given. In the problem, it's given as weight%, which is the same as mass%, flowing to a horizontal tube of uniform diameter at the rate of the flow rate is given 1 kg per second. It's heated from 300, so it is heated from 300 Kelvin to 400 Kelvin at 1 bar, same pressure. Neglect shaft work and changes in kinetic as well as potential energies between the inlet and the outlet. So let us see how that might be. So this is a schematic diagram of a shell and tube heat exchanger. So steam coming in, of course, that is not stated in the problem. Just I'm explaining. Assuming this is heated by steam. So this is the condensate which comes out. So and in during that process, it transfers the heat to the flowing gas here. This is the composition based on weight% is given, and the pressure is 1 bar at the inlet, and the pressure is 1 bar at the outlet. The temperature inlet is 300 Kelvin, and it is heated to 400 Kelvin, and the flow rate is given. We have to find out how much of the heat has to be transferred to heat it from 300 Kelvin to 400 Kelvin as a mixture of argon and helium. Not a single gas, it's a mixture of argon and helium, mixture of gases. Okay. Um, it tells you that the mixture exhibits ideal gas behavior that helps. The specific enthalpies of the components, that means argon and helium, in terms of mass. So it's kilojoule per kilogram, not mole, not kilomole, just kilogram. These values are directly given, and also sometimes they're given in terms of CP specific heat, but that is also not given here. Here directly the specific enthalpy values in terms of the mass is given here at these two different temperatures. So we have to find the value of Q dot. So what are the key? So at steady state, we have to calculate the value of heat input in kilowatt here. What are the key concepts? We are going to use steady flow energy balance for this heater, shell and tube. And we have to keep in mind that this is a mass fraction weighted enthalpy of an ideal gas mixture. That's what we have to calculate, and we'll see how we do it. At steady state, for a single stream, we know this is the equation, that this is the rate of heat transfer, this is the shaft work, that is for like pump and compressors, etc., which is not here. So this is equal to 0. This is the this is the mass flow rate of the mixture, and this is the specific enthalpy of the mixture of this, not a single component, specific enthalpy of the mixture in terms of mass, that is kilojoule per kilogram, and this is going out, and the specific enthalpy of the mixture coming in. This is the change in kinetic energy, and this is the change in potential energy. Since this is a horizontal tube, we can assume that this is a tube of constant diameter. We can assume there is no change in velocity. So change in kinetic energy is 0. And since this is a horizontal tube, we can assume this to be equal to 0. So if we neglect this one, which is already stated in the problem, this rate of heat transfer comes out. This is the molar mass flow rate of the mixture, and this the mixture enthalpy out, and this mixture enthalpy in. So this is this one, delta H mix. For an ideal gas, we can write the change in enthalpy of the mixture from 300 Kelvin to 400 Kelvin here is the weighted average of the change in enthalpy of each component, right? So we have to say this is a 300K and this is a 400K. So we calculate the value of delta H for helium to go from 300 to 400 Kelvin. We calculate change in enthalpy of the argon going from 300 to 400 Kelvin, and we multiply these two values by the mass fraction of each component. That gives you the value of change in enthalpy of the mixture. Okay, so these are already given. So here, delta H mixture would be equal to W1 delta H1 plus W2 H2, where 1 is for argon and 2 is for helium. So this is 0.5, 0.5. This is all, these values are already given here. These values are already given in this table. These values are already given here in this table. So we have taken directly from there. And one, so that is delta H mix is this one. So multiplied with this one, so it gives me 285 kilowatt. All the details are of course given here. Okay, so that's the amount of that heat that has to be transferred to heat the mixture from 300 to 400 Kelvin would be equal to 285 kilowatt or 285 kilojoules per second. So this is my answer. Okay. Note, for an ideal gas, always remember that enthalpy is a function of temperature only. For an ideal gas only, for an ideal gas only, that is true. Okay. Also, you can see that helium is responsible for most of the heat duty. So helium, that is almost 259. So okay, so it's responsible for most of the heat duty, whereas argon contributes very small to the overall change in enthalpy of the heat duty. Okay. What are the key concepts and lessons learned from this problem? First of all, reporting gas composition in weight percent basis, or which is the same as mass percentage basis, is unusual. Normally, ideal gas composition is expressed in volume percent, which is numerically the same as mole percent as long as we have the same temperature. I'll show an example. This 58% argon and 58% helium, we can just write this one as the molar mass of helium is 4 gram per mole, and of course argon is this value right here around 40. So we can calculate this one to calculate the mole fraction of helium as 91 and that of argon is 0.9. So 58% of argon and helium is the same as, or 50 mass percent of argon and helium is the same as 91 mole percent helium and 9 mole percent of argon. Okay. Uh, Helium-rich inert mixture is expensive and is used in specialized semiconductor and pharmaceutical industries. This is a very specialized one. For a single component, we have seen base mass flow rate basis. This is the equation what we have used. And assuming no shaft work and negligible changes, this is the equation what we have used and calculated this one. And delta H mixture is given by the weight fraction, weighted average of the change in enthalpy of each component. Just for the sake of completeness, I just want to write down for molar flow rate basis, we can write the same as the molar flow rate basis. Here is the molar flow rate, total molar rate of the mixture. And this is the change in enthalpy of the mixture per unit mole of the mixture. This is a change in kinetic and change in potential energy. So this might be equal to 0 for our case here. And you can see, assuming no shaft work and negligible changes in kinetic and potential energy. So this is the equation, which is almost the same what we have used, but this is on the mole basis. Okay. And change in enthalpy of the mixture is, of course, here, instead of the mass fraction or the weight fraction, we use the mole fraction. And here, this is expressed in terms of kilojoule per kilomole. Whereas in previous case, in our problem, we have used kilojoule per kilogram. Okay, so this is the change in enthalpy. Industrial application of this problem used mainly in electronics and semiconductor industries as a warm, inert purge or protective environments in high purity precious metal processing, fabrication enclosures, and thermal processing chambers on high purity reactors. Okay. So basically, so answer is we have seen is 285 kilowatt. So this answer is 285 kilowatt. So that's the answer.